So can everybody hear me now? Okay. So we're going to talk today about the tritium evolution from wires and foils. And this is some new work. Okay, you know, previously from everything that I've done, we went from wires to powder to wires to plasma. And now we're going back to some wires and foils. And there's my collaborators there. So the wires were here. We did these back in '93. We did some powder, attempted powder wires, and we switched over to plasma. The problem with the wires that we saw initially, these wires here, was that they weren't really pure palladium. So we had a total of 20 experiments that we ran with these sorts of 1 meter wires, 50 microns, and they weren't very reproducible. We had large amounts of tritium in 7 experiments from one particular batch. And then meanwhile, we started these plasma experiments because we thought that palladium alloys or palladium impurities were important and better producers of tritium. So since making these thin palladium alloy wires would be difficult and expensive, we just shelved that process in favor of the plasma technique, and that's what we've done. Just to recap some of these wire experiments, these were nominally pure palladium wires, but they weren't pure. Okay, and I put carbon in parentheses because we really don't know what that was. It could have been carbon, or it could have been moly disilicide or something else. I need to go back and analyze this impurity. But when you heated these wires with pulsed current, what came out were these spots, and they were really in spots. Okay, so they weren't pure, and they weren't very uniform. The microstructure of the wire also changed during the experiment, so you had sort of a moving target. You started out with this filamentary structure, and then you recrystallized that wire. So as you did the experiment, things would change. These were difficult experiments because the wire would come off the spoil, it'd expand, and then it would break at a terminating experiment. So it was a difficult experiment to do, and so that's why we kind of quit. However, these wires just used 250 milligrams of palladium, and we got a fair amount of tritium out of the system, 44 picocuries per hour per gram. These were fast, short, high-powered pulses. That's what we thought we needed to drive a non-equilibrium situation in that case. Also, some of them were run down in a tunnel with Steve Jones, and there we saw some neutrons, and we also brought them back and did the tritium. So the neutron-tritium ratio turned out to be 3 times 10 to the minus 8. So we didn't see any neutrons basically out of these systems. There were a handful of neutrons that you saw in the tunnel, nothing like 10 to the 6 that Larry was talking about from these nominally pure palladium. So then we switched over to plasma cells, so we have these metal foils and alloys. The reason we did the plasma was because we could load it. It was a non-equilibrium situation. We were forcing the deuterium in, and it didn't require much material. And we got some spectacular results from 4 component alloys. So these were very complicated alloys of palladium, rhodium, cobalt, boron. And that's good, but it seems to be that the palladium, that this plasma experiment, you're trying to force the deuterium in, and you're heating it at the same time, of course, because it's a 50 kilowatt pulse. And so it's coming out during it's diffusing out. Well, it's kind of a diffusion process, it seems like now, because the longer pulses tend to seem to produce more heat, more tritium. So we've switched over to looking back at these metal foils as we did the palladium wires. We just run a high current through there. Instead of 20 amps, we're running 200 to 500 amps through the nickel and palladium alloys. The nickel has the advantage that you can run it hotter. So this 500 amps through the nickel, it doesn't really care. The palladium, if you ran it that hot, you'd probably dehydrate it, so you have to run it a little cooler. So there's only 48 milligrams of nickel or palladium in there, and we're seeing something like 25 picocuries per gram. But it's a little bit more reproducible now because we do have a much more sensitive way of looking at for tritium. So we're using longer pulses, higher pressure, and HD mixtures in those systems, and that's what one of these foils looks like. So these are all alloy foils, or there's some pure palladium foils as well. So previously we used these Volonics. This is the Volonics graveyard here. They're a tube based system, and they burn out after a few years. Now it's all solid state switch, the energy storage, and then the high voltage or the low voltage power supply. So this is a much more compact system than what we had over here when we were doing this at the lab. This is also one of the things that we use for the tritium analysis. It's inline ion chamber. Has the advantage of being able to see the tritium as you make it. However, it's not as sensitive as a liquid scintillation counter. A liquid scintillation counter, you have to recombine that on a copper oxide bed and then count it. We typically will count it over a week, but the sensitivity is 10 times. So instead of seeing, maybe 7 out of 20 experiments have produced something, it's almost 100% now. There's maybe an odd one that broke early and didn't give any tritium. So we're much more sensitive, 10 times more sensitive. So this is the voltage and current waveform from one of those pulses. We're using a MOSFET pulsar. We're just dumping the 68,000 microfarad cap into the foil every 2.5 seconds. I'm not going to say that this is optimal because this is what we've done over the last few months. And I think probably we want to go to higher currents, higher current densities, and in much shorter pulses to keep the heating down so we don't melt the wires like we do. And so that's the ineffectual current pulse. Okay. Now some of the samples. This is a nickel alloy here. This is what it looks like prior and post processing. So you can see it does melt. And then over here you can see this is the pre-pulse sample. You see the rolling. And you see a faint grain here. After the process, you've expanded those grains. You haven't really enlarged them in the nickel, but the grains have popped out. This is with an HD mixture. So we haven't annealed them to any degree to where the grains would be larger. Now this is the really funny next slide, which I didn't collaborate with anybody on this. This is just one that we have, but this looks like everybody else's piece of palladium. Okay, you have these little rods that come up. It's a cauliflower structure down here on this one. So what's the difference between this palladium sample, which started out as this foil, and this palladium sample, which is still kind of a foil but has all of this growth on it? The difference is a slight difference in the pulse rise time and current density. And so you'll get a different, and this is the same material. It's a small alloy of mercury and iron was found in this particular palladium sample. These two are not the same, and this is probably a problem with, it's going to be a problem for reproducibility. If you ask me today, can I do this again? I'd say maybe. And if you ask me, can I do this? I'd say, yeah, I can do that all the time. Okay, which is probably not the one I want. This one was much better in terms of the tritium output than this guy here. But it's kind of remarkable that we've seen these features in every other experiment. So someone asked me at the last meeting, if there was a neutron, if we look for neutrons during these experiments, we do. The neutrons are looked for with a helium-3 detector, not a CR39 or any other kind of detector. Helium-3 is the gold standard for looking at neutrons. It's sensitive to thermal neutrons, maybe not as sensitive as to 2.5 to 14 MeV neutrons, but it's moderated. Helium-3 tubes are in here, and helium-3 is basically black thermal neutrons. So any fast neutrons that come in will get thermalized and absorbed into there, and you'll get a big response. So the detector efficiency that we have is 20%, and then typical background where we are is about 0.7 counts per second. So if we saw an output of 1 picocurie per hour, which is what we're seeing, we would be seeing something like 500 times the background if it were hot fusion. So we don't see anything over and above the daily variation in the neutron output, which is just due to the air pressure and temperature variations. This is counts per time, and you can see that it just kind of wanders up and down. That said, there may be some instances where we do see maybe a sigma or two of neutrons. So I'm just going to give you this is all pretty recent work on all these batches of wire. These are wires that were nominally pure, okay, different batches. They all have different levels of tritium output. These are all run at lower pressures up until here, and these are run at different deuterium concentrations, so 13% deuterium in the hydrogen. Then we started to run the foils, and the foils are all alloys, even the palladium foils, and they're 40 millimeters by 2 millimeters by 50 microns. Those foils tend to breathe, so when you pulse them, they'll contract, okay, due to Lorentz forces, and they're also hydrided. And so then after the pulse comes, they'll expand due to the hydriding. So they kind of actually move during the pulsing. They move quite a bit, and that's what tends to make that wire in the cauliflower structure. So these are the foils. These are the rates. These are the last two samples we ran, which are about a picocurie per hour, and those are nickel conetic foil. So it's a nickel iron. It's about 17% iron, and this palladium mercury iron alloy as well. And so there's one that didn't do anything, and that may have been a short experiment. And then there's a few that have various levels. All of these wires here would have been inert using the other system, so you have to use a liquid scintillation to be able to detect any tritium out of those. Some of these, like this one here, you could see it in the femtotech system, in the ion system. So during the period that we're pulsing these wires, we also look with a sodium iodide detector and some other detectors. And what we're looking for is any signs of radon contamination in the area, because there is always radon in these buildings that we're in, and that radon value fluctuates. So what happens is that we just use this as an indicator that we're clear of radon. This is an RM80 detector, and what we're seeing here is the temperature is the green line, temperature of the cell. That doesn't mean anything other than the fact that we're applying power to the cell. This is the room temperature back here. It's fluctuating a little bit. We don't have this temperature controlled. And here we're applying 50 amps or so to the cell. Here we've raised it up to 200 amps peak, and then finally it fails over here. This is the radiation output for that, rises starting with that, and then decays off, and then we typically see this. So what we've seen, this is pretty much similar to what we see from the plasma experiments, except the rise time's a little faster. And then after 10 hours, all the action is over. So the tritium we feel is correlated with this, and that's, you could run it for another 100 hours, and you might not get much more tritium out of these systems. So this is all very fast. Could be, as Peter suggested, maybe helium-3 burning from that. If you take the signal out here, and you take the signal near the peak, and you subtract those two spectrally, okay, what you see is this. And this is pretty much what everybody else sees. I think the Russians were the first to see this. But you see a drop, and by 250 kilovolts, there's nothing else out there. So this is a very low frequency, so low energy emissions. What you don't see here is you don't see a 600 keV peak, 638, or any other peak that would indicate radon. Okay, if you did, then that would be radon contamination, but we don't see that in this case. So we feel like this is pretty indicative of the actual reaction, whatever that reaction is. So the next steps would be to put this in a calorimeter to run at higher pressures, which we hope to do. We can't run at higher pressures right now because we still have it hooked up to the femtotech detector, and that is that pressure is limited to about 15 psi. So we'll put that in a calorimeter, we'll run it, we'll see if we see any excess heat. Typically with the plasma cells, we're seeing about 250 to 300 milliwatts for this 1 picocurie per hour output. And my conclusions here are that this nickel alloy is pretty reproducible. We've run a number of those, better than palladium. You saw what palladium did. The nickel actually can be run a lot longer before it degrades. And the tritium can be over several sigma. The effect can be attained in 1 to 2 days. So you can run this for a few, probably 20 to 30 hours. Then you can recombine that and then count it. Of course, you want to count that tritium for a week or so to make sure you've got the statistics down. And I resisted this for a long time, although we know that you have to have a non-equilibrium situation. But I think this is a diffusion-driven process, and I think McCubry and everyone else agrees that there's something going on. So it's diffusion probably across some surface. I don't know whether it's diffusion across the crack boundaries inside of the material or across the surface. And then if we can increase this X-ray or electron effect, we're not sure what it is right now. But if we can go up higher in current and then get a bigger signal, then that might be a good coffee break demo. So we haven't really this is pretty new work. We haven't really investigated all this parameter space. And I think I need to go back to the literature and look at what everybody else has done in this area, especially you, and see where we're at and what we can exploit. So this driver probably indicates that if we do make these multi-layer materials and we do have a number of interfaces, we'll see a bigger effect. So that's all I've got right now. I hope I didn't take too much time before lunch. Thank
you.
Yeah.
2 questions.
Okay, sure.
One, which kind of nickel alloy did you use?
It's a nickel conetic alloy. It's a
Nickel?
Nickel,
Cool.
iron, manganese, and I think that's it.
Copper?
No copper. Palladium copper did work in the plasma, but we haven't, we've only done a few alloys here with this. We did 40 alloys in the plasma. Palladium copper was one, palladium, rhodium, boron, cobalt, palladium nickel, those were active
Okay.
alloys, okay? So, we haven't done that much with this yet.
Okay.
Yeah.
Could you expand on this diffusion driven process? What do you mean?
Okay, so each one of these experiments that we've done has this component of diffusion. You look at the powder experiments that we did earlier, okay? We're heating the powder electrically, it's deloading, then it's reloading, then it's deloading, reloading, we pulse it. The wires, same process, back and forth, back and forth. The powder wire, same issues. The plasma's conflicted because you're trying to load it, okay, with the plasma, but you're also heating it. So you're loading and trying to deload. And then you're turning it off so it deloads. So this one I think is probably a cleaner way to show that it's diffusion driven. Diffusion across some surface. Okay. Yeah, what?
Did you measure the resistivity of that wire as a function of where you thought it was loaded?
No,
Okay.
it's tough to do. It's
I-
tougher than the other wire. The other wire we did, a
Okay.
long wire.
Yep.
This is only 50 milliohms, so it's a little
Oh,
bit,
yeah,
and you're
okay.
running large currents through it, so it's like 50 milliohms. The other. So, and that nickel, doesn't load much. So. Plus, it's changing its shape. Okay.
Right.
So
All bets are off.
bets are off. Yeah.
Peter has a question.
Oh, okay. Sure.
Few questions. What was the sequence of the pulses and what was the pulse width?
Okay, well, the pulse width, it was just strictly a spike. Okay, so the pulse width, if you look at that, it's maybe 5 to 10 milliseconds at that 200 amps, maybe not even that. Because it just goes up and back down.
Only one or?
Oh, no, that's, sorry about that. It's every 2.5 seconds to 10 seconds. So you have to let the palladium breathe, so you want to let the diffusion go in, so that's a 10-second process.
And what happened when you apply the calorimetry
We-
around the?
We haven't done that yet.
Oh.
That's that last slide. That's the calorimeter that it'll go into,
Okay.
okay? I don't expect to see much, but
And what was the maximum pressure that you?
it was 1 atmosphere, it was 760 torr. Okay, that's the big driver I think we're going to be able to manipulate that the current. Sure, Peter.
So nickel has terrible solubility for hydrogen and deuterium. How do you get any gas from nickel?
Right. So that nickel, when it's being pulsed at 500 amps, it's glowing. Okay.
So that helps
So
your
it's at
solubility
600
a
degrees.
little bit.
Oh yeah,
Do
solubility
you
is.
see any pressure drop?
The pressure actually goes up, during the pulse. Okay.
You have to possibly do thermal desorption for the hydrogen. It's, turns out, I was looking over Fukai's paper on vacancies in co-deposit material, and his diagnostic for it was thermal desorption in the case of nickel, the same thing with yttrium palladium.
Right.
There's thermal desorption things that tell you if you got the traps, and you can also get information, see how many of them, so forth.
Yeah. I'll tell you something later about the absorption, but we haven't done any of that here yet on the wires.
We have the possibility, if it's convenient to do.
So on the fuzzy wire, the wire with the cauliflower, the efflorescence coming off, that one, if you just take it out, it desorbs instantly. But measuring that is another matter, and so may have to heat it up to get that.
Right, the Fukai's thermal desorption peaks that were signified vacancy, it's something like 640 C and 800 C or something like
Yeah,
that. So
yeah. We've had our eye on that vacancy for a while, but we haven't. I don't know. Maybe that's something we should do. Any other questions? Everybody ready for lunch? Okay, great.
Well, we've run out.